So I brought you a presentation with some slides and some ideas. What I will mostly it's oriented to the past still, and to ongoing works, but because future is approaching now. But hopefully you will get some ideas what I'm doing here and what we will be doing in the group. It's incomplete certainly, but at least hopefully it will give you a flavor. So I gave a very generic title: multi-scale and multi-physics problems in porous media, homogenization and numerical model reduction. And the outline is as follows: a very short introduction at the beginning, and then I would like to discuss concepts based on different example cases, starting with uncoupled transport in porous media. And you will see this transport in porous media. This will be something which will continue on throughout the presentation. And the first simple cases will be a very simple example about chloride diffusion in concrete. The second case will be a bit more complicated. There it's hydromechanical coupling and transport related to that. Fluid transport in possibly, but not necessarily, fractured porous media, which we will treat by the means of computational homogenization and numerical model reduction. And there I would also like to dive a bit into some equations. The third part is about fracture and some ideas about how to handle that on multiple length scales. And last but not least, that's a bit maybe exotic, at least for my colleagues here at the Department for Civil Engineering, but here in MUSEN we are a bit broader. It's about exotic, it's about battery modeling, where there is some hydromechanical coupling plus electrochemical potentials. All right, and now I try to fit all these topics in a limited time. Let's see how it works out. Yeah, first introduction, and since I'm here now working in the civil engineering, civil and environmental engineering department, I brought, just to give an idea of what I would like to express, this typical example from civil engineering, a concrete bridge. And because this is nice, it contains multiple different length scales, starting from the structural length scale of the bridge with an order of magnitude of maybe several hundreds of meters. And then you can go down to the joints and to the plain concrete scale, then the concrete mesoscale, where we see the aggregates. Then we can zoom into the mortar scale, where we have small aggregates, and so on and so on. So obviously there are multiple length scales involved. And at the same time, also diverse physical processes are happening on those different length scales, and those ones who lead to damage, they're probably the most interesting ones. And there are many different processes, just to mention alkali-silica reaction, chloride ingress, and corrosion, which are of course somehow two sides of the same medal, and many others. And all of them, they need, to a certain extent, to a deterioration of the material on the different length scales. And obviously it becomes a problem if the damage, for instance, as a crack or fracture, is crossing the scales, because at the end, in the worst case scenario, this would lead to structural failure. But luckily, we have very good civil engineers who are very good in preventing that, obviously. Yeah, concepts for handling multi-scale problems, they're not super new, actually. They date back to the late 90s. And I would like to just give a short idea of the concept of computational homogenization. Sorry. And which is typically applied to two different length scales. One could extend to several one, but for simplicity reason, I would like to present here just ideas for two different scales. Basically, we have a large scale and a small scale, which we sometimes call subscale, depending on this length scale, sometimes micro and macro, meso, whatever, it depends where we are. But what is inherent as an ingredient to this idea of computational homogenization, to assume separation of scales. That means one scale is much larger than the other one. In practice, the question is, of course, how much larger is necessary. It's not necessary to have several orders of magnitude, but let's say, for simplicity reason, let's say 1 or 2. And by that, we might be able to introduce representative volume elements, which are typically cubes, which are considered to be complete in a sense and representative in a sense that they contain all relevant information that we need for the upscaling problem. And then the task is somehow to correlate the macro and the micro or large and subscale problems. They have to communicate. Some information is has to flow down to the subscale. This is typically done in terms of kinematic loading, which we call prolongation. And in the sense of, we call it the first order homogenization concept, if this is a linear relation in space controlled by macroscopic quantities and typically also a gradient from the macro scale, plus some fluctuations in the subscale. And then we could process this information here, for instance, by solving a boundary value problem, and the structural response has to be communicated back. And this is happening by means of volume averaging in this concept. Yeah, that's the basic idea. And now the thing is that we can apply that to multiple different problems. And just to show you how it looks in action, I would like to directly go to the first case, which has been part of the PhD thesis of Nele Pollmann at Chalmers, and together with colleagues there, Karin Lundgren and Kamyab Sandi. He's now at Stanford. And the idea here, the problem is chloride ingress in mesoscale concrete. So that means we have cement paste with very small particles, plus this is together gives the mortar, and then you have larger particles or larger aggregates, basically. And typically, what is observed typically is that there's a layer around those aggregates which is somehow pre-damaged, which comes from the shrinkage during the solidification of the concrete. And this zone is pre-damaged and typically has a higher porosity. And that's typically a zone where the diffusion takes place of the chloride ions in the absence of fractures at that stage. So, and here, since this is a surface effect that's also size dependent, I mean, the more small particles I have, the more surface I have, and the higher one can expect the effective conductivity for this chloride diffusion here. So at that time, we didn't have access to fancy 3D imaging equipment, so we were doing our 3D analysis on synthetic microstructures, just to give you an idea how to produce such a microstructure consisting of aggregates with a certain grading curve or size distribution. So typically we start then with dense sphere packing with a predefined relation of the radii of the spheres. This is used for a Voronoi tessellation or radical Voronoi tessellation, and from that we can then adjust the volume fractions, getting such aggregates. And actually, what we can do is that we really can design the structures in a way that they really lie between some bounds, design codes, whatever. So those ones we took from literature, for example. Okay, and based on that, now we can do our simulation. The model itself is not so super fancy here because it's just diffusion, but diffusion which takes in the volume plus at an interface. Without diving into the equations here, but what we can see, what I have displayed here is the ion flux in the case of an absent interfacial transition zone, so this pre-damaged layer. And here, this streamlined one where this interfacial transition zone is very dominant. And obviously, you can expect that here the conductivity will be way higher, or diffusivity will be way higher. And here we were able, based on these RVE studies, to introduce a very simple macroscopic material model, which we could fit to experimental data and then also could be used to predict for other examples the experimental data. So we were able to validate that. So this is the simplest case of a two-scale approach, because it's not really, maybe it's more 1.5 scales, because we don't solve a macroscopic problem here. We're using the RVE problem as a test vehicle, similar as we would have a sample in the lab, basically, and we extract macroscopic quantities, constitutive relation, and constitutive properties from that testing, virtual testing on an RVE. But of course, it would be nice also to be able to really solve problems on different length scales. And this I would like to show you for the next example case, where the physics become a bit more complex, because we induce now hydromechanical coupling. It means we have a solid phase and a fluid phase which are interacting, but we are using here a continuum model in terms of porous media, or pore elasticity actually in that case. Application we were working on is something from geophysics. In that case, a rock formation might have, again, different length scales here. This is the really the large formation where we have maybe different layers of rock, but if you zoom in, then you see that the rock is also somehow fractured. And if you zoom in further, for instance, sandstone, you also see that there's a pore structure, which is on a millimeter scale. The cracks can have tens of meters, so it depends. And one obvious application for that would be a geothermal heat production. In a geothermal reservoir, it's really wanted that there are cracks where water can be transported from one well to the other. That's the idea of geothermal heat production. So cold water is pumped in, is heated up and sucked out again. But for that, of course, fracture networks must be existing, or in case they're not there, then they have to be generated via hydraulic fracturing. That's not our cup of tea, but we would like to understand the properties of fractured rock as a mesoscale property. But still, these concepts could also be applied to concrete or geotechnical applications. The project I'm presenting you is a project together with Beatrice Quintal from Lausanne University and my former colleagues from Chalmers, Fredrik Larsen and Kenneth Runeson. And yeah, here I would like really to dive a bit into the equations. But I try to keep it as simple as possible. So the model I'm introducing here is very simple. It's linear pore elasticity. It means it's a linear but transient problem. If we consider cracks, these equations don't change terribly much. If we make certain assumptions for the pressure diffusion in the cracks, if we assume that there is a transport following Darcy law, which is basically means that you assume, for instance, a quadratic velocity profile in the crack, then the continuity equation we derive here will be very similar to that one for the porous elastic medium. That's why I skipped that to keep it simple. But okay, in pore elasticity, we have typically a stress which is defined as a solid contribution from linear elasticity and a fluid or pore pressure contribution, where alpha is a BO parameter somehow representing the compressibility of the fluid. Here, typically that's water, and even though water is widely assumed to be incompressible, here we have to consider it to be compressible because the bulk module or compressibility, the compressibility of water is in the same order of magnitude as the inverse bulk modulus of the solid grains and the rock. Therefore, we cannot simply neglect fluid compressibility. Fluid transport is controlled here in the simplest case by linear Darcy law, where this theta is nothing else than the pore pressure. Here we have a permeability, which might be anisotropic. And we define the storage term, which is representing the amount of fluid stored in the porous medium, defined as the porosity, plus the amount of stored fluid, which is due to a deformation of the pore scale. If the pores increase, then more water can flow in. Or if I increase the pressure, then I can also, in a compressible case, I can pump in more water. Altogether, the strong form looks like this: balance of momentum plus a continuity equation with appropriate boundary conditions and an initial condition. And we can pack that into, in the standard way, into a variational form. Here it's a space variational format, where again I have a coupled system of two equations. So far that's completely standard, because this is now what we typically would discretize with the finite element method and where we would be able to solve the problem. But now I have called that already fine scale model. So that's the model where I have all the heterogeneities. Heterogeneities in that case are not the pores and the grains. Heterogeneities here might be the fracture network, or might be that we have inclusions in the poroelastic medium with different material properties. Let's say some domains where the saturating fluid is air instead of water, or might be that the rock formation is weaker than the other one. So that's the type of heterogeneity we have here. On the large scale, on the total formation, we could do now on that basis a direct numerical simulation, but this would be way too expensive to resolve all these microstructural or mesostructural features here. Therefore, we would like to do it by two-scale analysis. So, and now we have to remember our ingredients we had. It was basically separation and scales, definition of an RVE problem, and this linear prolongation. And you see all these ingredients here. Let's start with the separation of scales. We introduced the separation of scales by defining running averages, which basically mean that here in my global equation, which is, of course, in practice, a point-by-point integration, I interpret each point, material point or integration point, depends if it's continuous or already discretized. Each point I define as something which an environment with something surrounding material, and that's my RVE actually. So in each point I attach an RVE, and in each point I integrate over the RVE. That's expressed by these running averages, where I have these angular brackets representing volume averaging, defining those operators here, or functionals. Then I have this communication, which I call prolongation of the macroscopic field to the subscale problem. With the linear approach for my variables here, I picked now displacement and pore pressure. This is the macroscopic contribution plus a fluctuation field. But the fluctuation field is something only existing on a small scale. I cannot control it that easy by macroscopic quantities. Now one can treat that a bit and exclude rigid body modes and so on. And finally, we would modify the first relation that U bar is removed. And this displacement gradient is only considered as the symmetric part. So classically epsilon in the case of small deformations. All these ingredients are now packed into our space variational format, which is a bit lengthy here. And now the trick is that we have now test functions which have a macroscopic and a microscopic contribution. And now we can test this form here separately for a macroscopic and a microscopic test function. And if we test only the macroscopic contributions, then we end up with the macroscale equation system, which looks like this. Not super much different, but this is now the global equation system where all the fluxes are now averaged quantities. For the stress, here we have the flux and the storage term, plus a non-local contribution, which I don't want to comment here further. And if we now test instead with only the microscopic contributions, we end up with the RVE problem, which we can find here. To get the RVE problem, boundary value problem solvable, we have to introduce some more constraints. In particular, this is the constraint on the fluctuation. And one very restrictive way would be to say that the fluctuation is suppressed at the full surface of the box. A little bit relaxed version is to allow for periodic fluctuations, which I would like to impose here. And also we need to say something how the macroscopic pressure is computed from the microscopic counterpart. For instance, this could be by volume averaging or by surface averaging. And altogether, we have a constraint weak form now. We have balance of momentum, continuity equation. Then we have the constraint for periodicity of the displacement fluctuation. Equation 4 is a constraint on the periodicity of the pressure fluctuation. That means we impose periodicity in a weak sense. And here we have constraints for these relations U bar and P bar, where for rigid body mode reasons we can remove that one for U, but this one is remaining. So if we are removing rigid body modes, then we have two equations with three constraints. Yeah, so this is now something we could use for two-scale simulation. We now have a macro-scale formulation and a micro-scale formulation. We know how they interact, and now we could establish a nested solution scheme, solving the macroscopic problem in each iteration step we call the RVE problem. In each single integration point, solve an iteration step on the RVE level and send the update back. But probably you already heard from how I explained that probably this is very slow, and it is because we have many iteration steps, and so this will kill us actually. So there's some strength. Maybe I start with the strength. The strength is, of course, that something which is really has full access to the microstructure. In principle, it's slow, but it's a straightforward implementation. And as long as one is considering only RVE studies, then it's rather inexpensive. For instance, for this virtual testing, what I showed in the very beginning. But the weakness is, as I said, as soon as there's something non-linear, and also the transient properties at least make it turn into an iterative problem, then we have to solve in a nested fashion, which very high computational costs, and very also not to neglect the high memory usage, because for all the RVEs, the history must be somehow stored. So this is rather complicated and expensive, and in practice limited to academic examples. And we need more efficient approaches for real-world problems. And the basic idea is, of course, it would be nice to have more pre-computation in an offline sense and more online and less online computations, which are the expensive ones. And one way of doing that is numerical model reduction. And I would like to present here in very briefly how we do that in that case, based on a snapshot PUD for proper orthogonal decomposition. And the first thing we do here is, as I said, this example is not super complicated because it's transient but linear. The first thing what we are doing is we now introduce an alternative decomposition where we decompose all quantities in a stationary and a purely transient part, because the stationary part is linear. Linear is always nice, but it can be pre-computed. Okay, then we only need to solve the transient problem. So, and the treatment of the transient problem is now as follows. We introduce an approximation for this transient pressure field here, which is a linear combination of pressure modes times mode activity coefficients. And the goal is to have this sum here, that the dimension of the sum is really low, maybe that we only need a handful of modes. And actually that's possible, but we need a technique to extract the relevant information. And this extraction of the relevant information, that's done by the proper orthogonal decomposition. So in practice, what happens is that we run on the RVE level training computations on this box with several loading cases. We extract snapshots, and then those snapshots are the input data for the proper orthogonal decomposition, and basically it turns into solving an eigenvalue problem. And the largest eigenvalues correspond to the dominant pressure modes. And then we truncate after a few of them, and typically one can show that really few modes are sufficient to contain all the relevant information. And that's why it becomes way cheaper. The good thing is now that all quantities, depending on these pressure modes can be again pre-computed. We call that sensitivities, which can be pre-computed after the training. That means they are out of the online phase. Okay, but now we have to see what happens to the equations. And first of all, we assume that a similar decomposition could be done for all quantities. We are interested in displacement, and the Lagrange multiplier means the fluxes. And then we put everything into the continuity equation. We do some massage of this equation. And the beauty is that what comes out is basically an evolution equation for those mode activity coefficients, which are the unknowns here in this transient problems. And the entire transient problem is reduced in solving an evolution equation for these parameters psi, where all these system matrices can be pre-computed. These are sensitivities on the pressure modes. And it can be further simplified in the spectral format. Then it looks like this, where C is a diagonal matrix, so it's really a decoupled ODE system. And finally, this is, has the same structure as the Maxwell-Sena rheology in viscoelasticity. So therefore, we also call this resulting large-scale model poro-viscoelastic, actually, even though the mechanisms are not comparable to classical viscoelasticity. So basically, that means that solving the two-scale problem means online solving the macro-scale equations. And instead of solving the AVE problem, we only solve on top of the macro-scale equations a local ODE system. That's why it's way cheaper. And just to give you an idea about the speed up, I brought you an example here, which is more related to geotechnical engineering. It's a consolidation test with some inhomogeneous loading here. That's a loading plate here. And this body here has a length of 10 meters and a height of 20 meters. It's consisting of material with some hypothetic inclusions, where the inclusions have different material properties. But the important thing is that those inclusions are way smaller. They have a radius of 2 centimeters. And actually, if we would resolve this fully here in this domain, if we would do a direct numerical simulation, then we would need to resolve something like 2 million of those inclusions. So that's something, obviously, which is rather expensive. But with our reduced two-scale approach, we can do it way easier. So these are the results from the two-scale simulation. Here, this would be the fluid flow after 60 seconds after this loading. And this would be 1 hour after the loading. And we see that something happening here. The fluid is escaping this pressure zone and so on. But the most relevant information is here in the red box. It's the computation time done on a standard computer, nothing special. And for the direct numerical simulation of one AVE, which is consisting of several 100,000 of degrees of freedom, we need to do that for training, for sure. Okay, this takes a couple of minutes. If we resolve that, this would be the direct numerical simulation. But in the online phase, this is reduced to solving an ODE system. And this is maybe, I'm not sure if it makes sense to give 2 seconds, because that's probably only the initiation of the problem. So this is almost not tractable. But if we now come to the full consolidation test, then the reduced FE² model only takes, again, a couple of minutes, 8 minutes or something like this. Whilst the direct numerical simulation, we couldn't do that here on a standard computer because they couldn't resolve these 2 million of inclusions. So there's a massive speed up in that case. And this is definitely a strength because we only need to solve the macro scale problem plus the ODE system in the online phase. The rest is offline and pre-computation. What is nice, that's a very straightforward extension of the FE² concept. And in similar fashion, this could also be done for other problems. For classical examples in literature are for viscoelasticity, plasticity, viscoplasticity. But it's also done, I don't show it here, but we also do that for these electrochemical processes. And one nice feature, I don't want to go into detail, is that it's also possible to estimate the NMR error, so the error associated with the reduced basis. Weaknesses, I mean, I have said that this is a transient but linear problem. This could also be similar, this concept could also be used for nonlinear problems, but I mean, as more path dependent or history dependent, this becomes the worst is the quality of the approximation of the reduced model. So it's for mild nonlinearities, this is also possible, but this is limited to a certain extent. A second disadvantage and drawback is that we do the training once in advance. In that sense, we could call it an a posteriori approach. When it comes to enrichment and adaptive enrichment of the reduced basis, that's limited. And in the extreme case, a model update would require a new training. So in that sense, there are some applications where this is not, the speed up is not sufficient. In particular, when it comes to online control of systems, if it's an inverse problem where we need to have very fast forward simulations, and also in optimization when it comes to augmented reality and also handling a huge amount of uncertain data, then other strategies might be necessary. And that's something we are working on also, and we will continue to work on. And therefore, I'm very happy that soon there will be some more people in the group. Fredrik Ecke, who will defend his PhD thesis next week, he will be joining the team in September as a postdoc. And he, besides this, works on estimation of the NMR error. He will also continue, or he will start to work on a method which is called proper generalized decomposition, which is an alternative concept to approach real-time simulations. And we would like to continue also here in this domain of porous media. Just an outlook on in this geophysics application. Before later on, I will also talk a bit more about some applications in civil engineering and environmental engineering. Where we would like to use that is also in a joint project with Beatrice from Lausanne and Eric Sänger from Fraunhofer in Bochum. Is that we would like to do inverting of seismic data. That would be Eric's part, and Beatrice and we would work on the type of inversion of the RVE problem. And basically, what we are interested in is the properties of fracture networks. And why is this so interesting? I have already mentioned that a couple of minutes ago, but you have to imagine what happens here in such a problem. Here, this is cross-hole tomography, which means we have one borehole here. You see it's rather deep, going down to more than 1 kilometer. But geothermal applications would be even deeper. Here would be the second one, and basically in one borehole for cross-hole tomography, there would be a line of sources for seismic waves. And on the opposite side, there would be a line of receivers. And this is now basically a technique. I'm not an expert in it myself, but basically there's a technique to really screen this domain layer by layer and then to invert the data. And the relevant data which can be extracted is the stiffness or wave velocity in that case. And it's also possible to make conclusions for the attenuation. And the attenuation is exactly a property of those fracture networks. I mean, what's happening is if a seismic wave is traveling through such a fractured medium is that the cracks are compressed in an inhomogeneous fashion, which means that water is squeezed out into other fractures if there's a network. And this squeezing out is dissipative. So that means a certain frequency content of the wave is filtered out, is attenuated. And that's a relation we would like to understand, and there we must become more efficient in simulation. Yeah, a completely different concept on the first look is fracture. Well, I talked about fracture, but here it's about fracture propagation in a multi-scale context. This is certainly relevant in many, many different applications. Here, I would like to introduce a very, very simple case. It's a part of Ritu Keshwarali's PhD thesis, who will also hopefully soon be enrolled at TU Braunschweig in our group here. I would like to show the very basic example of brittle fracture in a linear elastic material using phase field fracture modeling. So in that sense, it's very much in line what Laura de Laurentiis was doing here for many, many years. And now we would like to do that on several length scales. All right, without going into detail, there are many different ways of writing down the constitutive relations and the equations here. And basically we have a degradation function, which is somehow measuring the damage state, which is this phi here. Which is under tension, reducing the stiffness of the sample. We treat this damage variable in a gradient sense. That means we have here a flux of this damage, and also if you have a storage term here. And here is the tricky part, the history variable, which is somehow taking care that the evolution of the damage is always positive. It means the damage should increase, there's no healing. Okay, that's by itself a huge discussion in the community, but that's maybe not my point. I would like to see how such a formulation can be introduced on two scales, how this can be interpreted on two scales. And this is not obvious that this is possible, because actually, even though we have here a smear damage model, damage in a fracture propagation is still a localization of a property. So we have still a local damage, even though it's smeared out. But compared to the sample size, this is, of course, still local. And this is not that easy or that obvious to see how this could work in a concept where we have an AVE on a small scale. So that's what we wanted to find out. And so we took our machinery and started our machinery, deriving the weak format and starting all the ingredients, separation of scales with these running averages here. We have this linear type of prolongation, first order in a first order homogenization sense for the displacement and the damage field, which means that we have a macroscopic damage field and a gradient of macroscopic damage field and a macroscopic strain as the macroscopic loading. And just as a side remark here, we also considered the case that there is no macroscopic representative for the damage and no macroscopic damage gradient, which means that this macroscopic contribution is simply zero. Then we put everything into the weak form. We start our testing of macro and microscopic properties, and we end up with the macro scale problem here in the blue box, which has its equation system has the structure of a phase field fracture model again. But what's quite fancy, if we assume the absence of macroscopic gradient, then we only end up with this weak format of the balance of momentum, where now the damage effect is somehow hidden in how sigma bar is computed. And this is nothing else than a local damage model. So we have here a switch where we can say, okay, we would like to have a local or non-local macro scale damage model. So, and then this can be used for RVE studies with various types of boundary conditions. Because I'm talking too much, maybe I can keep that short here, and then we see that the choice of boundary conditions, the more restrictive it is, the more stiff the behavior in this stress strain curves will be. Maybe that's just a side aspect. And now we were interested in the two-scale behavior, and since this is really expensive, we ended up really with a Mickey Mouse problem here, but it was to illustrate how it works and that it works at all. So basically we have here a bar. So again, I would call it 1.5 dimensional, because there's only one loading direction actually on the large scale, whilst the subscale is two-dimensional. And here we only have a few elements where one element is a bit small, the diameter is lesser, so that we have something like a notch there. So we can define that where the the crack has a chance to localize, because that's needed anyways. Okay, and now we tested the two concepts, the one with it, which is localized or with the local model, and the blue one with the non-local model on the large scale. This is now the macroscopic stress-strain response. You see there's still some wriggles here related to Merkel stability, could be smoother. And essentially what one finds, even though it looks rather similar, is that the non-local model has a bit higher resistance against this crack propagation, the black curve compared to the local model, the red curve. And what we were interested in is to see how this localization occurs. And here on the left-hand side, you see that for the evolution of this damage for the red curve, so we're starting with this light blue state where damage increase only in one element, the one with the notch. And then if you proceed following this curve into this collapse, into the light purple, we see that the damage is only growing in one element. That's a classical local damage model, actually. And in a non-local case, then we're following this black path from the green, orange to the dark purple, stage. And then we see that damage is growing everywhere, even though more here, but you see that there's certain profile. That's what we typically would also expect for a non-local damage model. And what is interesting here is that, I mean, on the small scale, we associate full damage with the damage parameter being equal to 1, whilst this is not the case here. Here, full damage means damage is equal to 0.25, and for the non-local model, it's even lower, it's lesser. The reason is how this phi bar is computed. It's the volume average of the damage in the RVE. And if I have a crack passing through the RVE, the volume fraction, so to say, of this crack is, of course, smaller than 1. That explains, I'm sorry, I'm speaking too much up in front of the screen always, sorry for that. So that's why this value is lesser than 1, but the interesting thing that this is something which is self-regulated by this two-scale iteration. Yeah, some outlook on what we would like to do here at the Institute. It's not only modeling, but also, of course, we would like to increase our knowledge in modeling, but also in experiments and for multi-scale fracture. And therefore, Roland Kruse was already pimping a bit the equipment we have. So actually what we want to do in future is really to have multiphysics crack initiation and propagation. In view of concrete, interesting tasks are here, accelerated corrosion of reinforcements, and based on that, those cracks or the zones, damage zones around the reinforcements, if water is entering there, freezing, thawing cycles, because then this might lead to frost damage. And apart from the modeling side, we also would like to do 3D imaging of that. So Roland Kruse was starting to build a prototype, and actually that's how it looks at the moment in our macro city. Where you see basically here, that's the rotating stage. And here it's not easy to see, there's a Peltier element, and so we can cool down and heat up the sample. The sample would be placed here on top of this piece here and put into a insulating tube. So this is something we can then manipulate in the microcity in situ. And here the pipes, that's we need for the cooling of the Peltier element actually. So this will be also, there will be also some more stuff working not only in the lab, but also on modeling. This will be Knut Andreas May, another postdoc coming in from Sweden by September this year. Yeah, and actually, Roland was already trying out some very first examples here to see if we are able to really to have fracture in concrete related to frost. This is without corrosion so far. And actually, this is very fresh data that's not much made of. That's just the raw data we see here. So this is a concrete tube which has a diameter of roughly 8 millimeters. And there's a borehole here. We drilled the borehole in with a diameter of 3 millimeters. And this is filled with water. Whilst we are at the moment not really sure yet how it penetrates the concrete, we cannot, that's too early to say. But we were here interested in what happens in this borehole, actually. And at least we succeeded in a way that we could already now observe in the first glance 2 different damage mechanisms. The first one is here that this surface was deteriorated, and you see all these pieces here which are falling down. That's something like a microscale damage. And at the same time, we can also observe here a crack, and it's not that easy to see how it continues here. It's really going through the entire wall of this cylinder. And in the top view, we only see that it's not only at the bottom, but it's really going down from the top to the bottom. You have to, it's here. I think the video quality is pretty poor, but maybe you can recognize it, that this crack is, now we're walking from the top to the bottom of this cylinder here, hollow cylinder. So this is just first impression, but it's nice to see that we can already produce something with our prototype. Yeah, and since time is running out, very short, very few words only on a completely different field where the hydromechanical coupling is enhanced by some further physics. It's by an electrochemical potential, which is application which is called structural battery, which is a very special type of a lithium-ion battery. Goes back to a colleague from Chalmers, Leif Asp, and his PhD student, David Karlstedt, and also a PhD student of mine, Bin Tu, is working on that. Hopefully, he will be also re-enrolled in Braunschweig after summer. The idea of structural batteries, in very short, is to use components which are already built in a composite, which is basically carbon black fibers, and the idea of Leif and co-workers is to use those carbon black fibers as battery electrodes, because they are there anyways, and why not giving them a second functionality? And what they developed is a concept that looks like this. You have the different stacks of carbon fibers in a bit simplistic visualization here. Maybe it's better to look at that here in this 2D plot. So one part of the electrodes of the fiber, is coated by lithium-rich particles. In that case, the fiber is acting as a collector of the current, and the electrochemical process happens here in this coating, where lithium particles are set free if the potential is like this. Here's the separator in between, and here are the second electrode, the negative electrode, where lithium ions are intercalated. That means that they enter the carbon black, and they take interstitial places in this carbon black structure. So, and the funny idea that's built in, and just to give you an idea why this is a porous medium, and just look how the separator looks. That's a polymer, which is not active electrochemically, but it's filled with a liquid electrolyte, where the lithium diffusion takes place, or lithium migration takes place. On top of that, this structure is deformable, so there might be something that we call it convection, so a motion related to this, the deformation of the pore scale. And here, just to show that this is not only dreamt up, they can even produce it, so it's somehow working. But for us, it's of course a very, very fancy application to test our tools, our numerical and modeling tools. And just without any equations here, just to give you an idea how it looks here, you see that's again a two-scale problem where this could be considered as an RVE. The fibers are here, and these pore structures is way smaller. The pores are of the size of 200 nanometers, whilst the fibers are diameter of, let's say, 5 microns. And so if this is now undergoing a discharging current, basically, plus a bending at the same time, which is this peak. And now when we have compared here models considering the convection of the liquid electrolyte, that's the black curve, and the blue curve is without this convective part, and you see then clearly that this is a relevant process here. All right. Something we would like to continue in future is not only the application as a battery, but it's also can be used as an actuator. And this is also quite a fancy application. I like it a lot because, I mean, the idea is if the lithium ions are intercalating the carbon fibers, which happens that they expand. They expand by 3 to 5% in thickness direction, and also 1-2% in longitudinal direction. And if this is oriented in a right way, this leads to a bending of such a composite. And this is, of course, could be used as an actuator. And last but not least, also here we would like to combine modeling with experiments in the lab and enhancing our in situ tools. And what we are interested in is here what we call electrochem-mechanical fatigue. So what happens to a battery or an activator in such a setup after a number of charging-discharging cycles under this mechanical loading. So I hope I didn't talk too much. As I said, this is just, it's maybe not a full picture. And as you have seen, I mostly referred to colleagues from Chalmers and other places. And now I'm really looking forward to see how this can be incorporated here in the framework at the TU Braunschweig. And yeah, maybe you have some ideas how to continue and how to interact, and I'm really looking forward to that. Okay, then I'm finished, and I would like to thank you for listening to me.